we were making that the change of force between two objects was happening instantaneously without any loss of time. F1 was changing to F2. And according to Mr. Einstein, according to special theory of relativity, we know nothing can move faster than light. So not even the graviton. Graviton also is not allowed to travel faster than light. So if it travels with the speed of light, then when you change the distance between two objects from R1 to R2, even earlier there was an exchange of a graviton, even now there is an exchange of a graviton, but this graviton cannot move faster than light. And therefore, the time elapsed in the change from F1 to F2 would be non-zero, positive, definite, howsoever small. Okay? It cannot happen instantaneously. It cannot happen with a zero time difference. Okay? This is the main point. So, would you like to just naively, if something comes to you, because then I may be able to tell you better. Right now, I'm just giving you some physical motivations of how to. For me, this is the simplest way to look at things. Another thing that I had told you was the thought experiment, where I made two protons collide with each other, and each one was accelerated at a very, very high speed of the order of 10 to the power 18 times the rest mass times c square. Okay, so both of them accelerated to that. In CERN, they would have it much less, maybe 10 to the power 3 times mc square, maybe 10 to the power 4 into mc square, even with the improved energies at CERN. So you can imagine how far we have to go. Okay, I'm talking of 10 to the power 18 times mc square. So obviously, you have to go to much higher. I don't think even in your lifetimes it will be reached. Certainly not. But one day maybe people would be able to do it. Okay, you keep upgrading your things, and because a lot of technology is needed. You see, it's not as simple as we think. You see, you have to correspondingly upgrade your entire technology. Okay, it's very easy to talk about thought experiments, but it's very difficult to realize them. Okay, so even upgrading the energy 10 to the power 3 into mc square to 10 to the power 4 mc square is huge task, or to 10 to the power 5 times mc square and so on. So think of going, but an ultimate theory of nature, if I could think of, must be in a position to explain the outcome of this thought experiment. Okay? Where gravitational field strength becomes equal to the electromagnetic field strength or any other field strength. So we don't know what happens at that energy scale, but we can't rule out and we can't stop our mind from thinking. So we must find something, okay, which would always work, even at low energies, even at high energies. Okay, so this is the point, and another important point is the Heisenberg uncertainty principle and the zero-dimensional objects, and then we realize that this vertex, considering 3 world lines, to which each world line corresponds to the motion of one particle, which is zero-dimensional. The vertex is also zero-dimensional. Okay, and so this works perfectly nicely for strong interactions, for weak interactions, and for electromagnetic interactions. Why? Because Heisenberg uncertainty principle smears out the singularity arising at r equal to 0. But for gravitational interaction, it does not work. Okay, that Heisenberg uncertainty principle, as we know it, would not work. Okay, we would try to modify it to take into account this Planckian length scale of 10 to the power minus 33 centimeters. But prior to that, we have to assume that we are going to replace the notion of zero-dimensional particles with one-dimensional objects called the strings. And that would, to me, would be the birth of the idea of string theory. Okay, so whenever some experimentalist or anybody happens to ask me, so but you don't see anything about string theory in nature in the experiments or at CERN or at I say no, I don't worry about it. I don't have to find. But it's a correct idea. Because unless I assume this, I have so many difficulties and I'm not able to resolve them. If I want to resolve them, I must do it. Okay, it doesn't matter whether you discover it at CERN or not. It's of no consequence to me. Okay, so that's the answer. Okay, now we can go a little bit further. We still have some time. So let me tell you a few things from. This is a physical motivation. Let me now tell you how do we go about it from mathematics point of view. Okay. Yeah. Now, could I remove some of these things? Yes? Very good. Let us do a little bit of classical mechanics and let us see how can we extend and why should we extend the ideas that we learned there to more sophisticated things like we want to do. Okay, so let me consider the Lagrangian of a non-relativistic one-dimensional point particle. Okay, very simple thing that we do at the first year level. Very good. So this is T minus V and this is 1/2 mx dot square minus V, and this V is 0 for a free one-dimensional particle. Okay, one-dimensional. Let me put it here. One-dimensional free particle. Free particle would mean potential equal to 0. Okay. We make a very simple case. We put the potential 0. So there is only kinetic energy. So kinetic energy minus the potential energy. This is just 1/2 mv square. Okay, 1/2 mv square. And so your action would be ln r dt one-half mx dot square, and now I will obtain the Euler-Lagrange equation to be very simple, the Euler-Lagrange equation of motion, and now I would use this L, and what I would get, this guy, there is no x here, so this term is 0. This is 0 minus dy dt of del x dot is 1/2 into m into 2 x dot. So this is minus m x double dot or minus m dy dt of x, and this is 0. So it tells me that dv by dt equal to 0, m is non-zero. If m is non-zero, then this guy is going to be 0, right? Very simple. So this is 0, and this implies b equal to x dot equal to the constant. B equals to the constant. So it tells me, it does tell me that yes, if I consider a non-relativistic, simple one-dimensional particle which is free, has no potential, is not bound by any potential, then my V is equal to constant. But it does not tell me what is this constant. This could be a constant, let us see C. This could be a constant 2C or 10C, which is the velocity of light. This is still constant. It could be any. So it could be greater than C. So this is the problem that I encounter. If I consider a classical particle in one dimension, which is free, not bound by any potential, I get V equal to constant. And this V could be anything greater than the C, velocity of light, speed of light. It could be more. Therefore, I cannot use this. This cannot be the correct Lagrangian to describe a relativistic particle. Obviously not. If I were to describe a relativistic particle, what would I do? I would certainly like to see, first thing I would like to realize that no, this is not the right way to do it. I must have the correct Lagrangian. Okay, very good. So this is one thing. And what I would do now is, I'm going to have Xn equal to L dt, okay, and this is